The fourth type of first-order differential equations is the linear DE, where the general solution would have to incorporate a particular format using an integrating factor. Learn more about it here in Engineering Math 5. What makes linear differential equations distinguish from the other first-order DEs? Say we take the standard format of a differential equation having a multiplied by the derivative of y with respect to x plus by is equal to cx, where a, b, and c are all in terms of x. If we isolate the derivative by dividing the whole equation with a, and then denote b all over a as p, and also c all over a as q, we can get the format of a linear differential equation, which is derivative of y with respect to x plus p in terms of x times y equated to q in terms of x. Such simplified format is the differential equation, which is linear in y. So we can also take a dE linear in x as dx all over dy plus p in terms of y times x, which is equal to q in terms of y. The general solution for linear differential equations incorporates a formula, which states y times an integrating factor is equal to the integral of q of x times an integrating factor times dx, where the integrating factor is taken as e raised to the integral of p in terms of x times dx, or p in terms of y times dy, when we are working with the other variable. It is obvious at this point that the identification of p and q is important in the solution. Here is the first example with the differential equation 2 times the quantity of y minus 4x squared multiplied by dx plus x times dy is equal to 0. The first step is to check on which derivative the equation is linear with. Let's try dividing everything by d of x to make dy all over dx. The first term will cancel out dx, and the second term will absorb it as the denominator. And in order to align the equation to this standard form, divide it again with the coefficient of the derivative, and that is x. So the simplified format turns out as dy all over dx plus 2 all over x times y is equal to 8x. And from here, we can identify 2 all over x as p and 8x as q. It is noted that such terms are of x. An important part of the general solution is the integrating factor, which is solved as e raised to the integral of p dx. Replace p with 2 all over x as identified previously, and move on by extracting the constant 2 out of the integrand. Next is to take the integral of dx all over x, which is the natural logarithm of x. Then, using laws of logarithm, manipulate 2 ln x as ln of x squared. Then remember that e raised to ln can actually cancel out, giving us the integrating factor as simply x squared. The general solution is y times the integrating factor is equal to the integral of q of x times the integrating factor times dx. So y is multiplied with x squared, and this is equal to the integral of 8x times x squared dx. Simplify the terms and extract the constant out of the integrand to have x squared y is equal to 8 times the integral of x cubed times dx, and we are ready to integrate. So the integral of x cubed is x to the 4th power all over 4, where 8 and 4 cancel each other. Thus, the general solution is simplified as x squared y is equal to 2x to the fourth power plus c. Example 2 is with the differential equation y dx plus the quantity of 3x minus xy plus 2 multiplied by dy is equal to 0. Work out with the standard form. So let's attempt to divide everything by dx. We get y plus the quantity of 3x minus xy plus 2 multiplied by dy all over dx is equal to 0, where although we have plain y on the first term, we have a quantity which would be multiplied with dy all over dx on the second term, making the equation more complicated. This shows that the dE is not linear in y. Let's try dividing everything by dy, where the second term will be simplified. The outcome is y times dx all over dy plus 3x minus xy plus 2 is equal to 0, which has 4 terms, but let's still continue by isolating the derivative, so we divide everything by y to make the equation dx all over dy plus 3x all over y less xy all over y plus 2 all over y is equal to 0. We still have 4 terms after the last step, so attempt to group some terms together. Note that 3x all over y and negative xy all over y have the same denominator, so let us group these terms. Next is to extract out x from the group to have dx all over dy plus the quantity of 3 minus y all upon y multiplied by x is equal to negative 2 all over y. Then simplify further y all over y as 1 to get dx all over dy plus the quantity of 3 all over y minus 1, everything multiplied with x, is equal to negative 2 all over y, where we have the quantity 3 all over y minus 1 as p and negative 2 all over y as q. Take note that p and q are in terms of y. Let's continue with the determination of the integrating factor using the formula e raised to the integral of p times dy. Plug the quantity of 3 all over y minus 1 for p and then integrate them individually. So 3 goes out of the integrand again, and dy all over y is integrated as ln of y. Then the integral of dy is y. So the integrating factor is computed as e raised to 3 ln of y minus y. Again, use logarithmic laws to manipulate the exponent. E can be separated according to the exponent as e raised to ln of y cubed times e raised to negative y. And again, e raised to a natural logarithm will cancel each other out to leave y cubed. Thus, the integrating factor is simplified as y cubed times e raised to negative y. Now that we determine the integrating factor, let's plug it into the general solution. Remember to switch variables as this example is linear in x instead of y. So we have x times the integrating factor y cubed times e raised to negative y is equal to the integral of q, which is negative 2 all over y multiplied by y cubed times e raised to negative y dy. Simplify the equation where the outcome is x y cubed times e raised to negative y is equal to negative 2 times the integral of y squared times e raised to negative y dy, which will be integrated using integration by parts. Going back to integral calculus, if we have an expression, the integral of u multiplied by v prime, integrating it by parts will follow a format of uv less the integral of u prime v. Now break the expressions into parts, like u will be y squared and its derivative is 2y times dy. The rest of the expression is e raised to negative y dy, where this is denoted as v prime. Integrate it to have v as negative e raised to negative y. So the whole expression will be integrated into the two parts following the format where u is y squared times v, which is negative e raised to negative y, minus the integral of u prime multiplied by v. Then everything is multiplied by negative 2. Simplify the first term where the negatives cancel out. 2 is the constant with y squared multiplied by e raised to negative y. The constant negative 2 is also distributed to the second term, which is the integral of negative 2y times e raised to negative y times dy. If we take out the constant in the second term, we then get the final expression as 2y squared e raised to negative y minus 4 times the integral of y multiplied by e raised to negative y times dy. The whole solution after the first integration by parts became simple, but it still requires another integration by parts on the last term. So again, denote u for y and its derivative is dy. The remaining part of the term is denoted as v prime, so integrate it to take v, which turns out to be negative e raised to negative y. Following the formula, uv is y times negative e raised to negative y minus the integral of u prime v, which is dy, multiplied by negative e raised to negative y. Do not forget that the whole expression is multiplied by negative 4. Simplify both terms to make 4y times e raised to negative y plus 4 times the integral of negative e raised to negative y times dy. Now the integral of negative e raised to negative y is determined, so we get 4y times e raised to negative y plus 4 times e raised to negative y. So by collecting all terms from the integration method we used, we come up with xy cubed times e raised to negative y is equal to 2y squared times e raised to negative y plus 4y times e raised to negative y plus 4 times e raised to negative y plus c. Multiply everything with e raised to y to cancel parts of most terms and simplify the answer to xy cubed is equal to 2y squared plus 4y plus 4 plus c times e raised to y.